Okay, so in office hours today, I just answered a bunch of kind of theoretical questions without recording. Sorry. And what most of us are looking at right now in office hours is the report form corrected calculations. I did go over this in office hours yesterday and in the gas stoic lab video that's posted to Canvas, so if you want to look at those locations, that's great as well. But here's essentially the thing that we're looking at. We've got some experimental setup. We've got an eudometer. It's this funny upside down piece of glass. And at first it's full of water. And we've got the atmosphere pushing out here. And that's what's keeping the water up inside the tube. Now there's a limit to how high that water column could be above this water level. But if we don't have anything in there, it's going to be pushed all the way for the eudometers we have. And then we do some chemical reaction. We capture that gas. I have a tendency to make this too large, but here we go. We capture that gas, and now we've got some pressure pushing down inside of there. That pressure still is not equal to the outside pressure because you can see this level inside the tube is not equal to this level outside the tube. So we've got some water height there. That lets us know that the atmospheric pressure outside is not the same as the pressure of the gas inside. So the question becomes, well, how do we best represent this, the pressure inside? And what the experiment asks us to do is it first says, pretend that the pressure of the atmosphere is just equal to the pressure of the H2 gas. Let's pretend like it's just perfectly that. And when we do that, we're ignoring several different components. We're ignoring the fact that there's liquid water and that there might be other gases inside the tube. So if we do that, we actually get an overestimation of our H2 gas produced, because this calculation would say that this whole space, outlined in red, that whole space is filled with hydrogen gas. Would be saying, oh, it's just like this calculation. And that is experimentally not what we see. So if we want to get the actual pressure, the thing I have written in blue there, we'd have to say, okay, so my pressure of the atmosphere is going to be equal to the pressure of the H2 gas that we collected, that we know we collected. And it's also going to have included in it some pressure from that liquid component, right? From this water. Water interacts with gravity. There's going to be some force over area there. And that's going to give us some pressure associated with that. So we're going to have some H2O liquid pressure. And then we can say, well, is there anything else we need to include to account for this pressure? Is there only one gas up there, or is there, or are there multiple gases up there? And if we look at our chemical reaction, we have magnesium plus HCl, this is solid magnesium, plus HCl aqueous goes to magnesium chloride aqueous plus H2 gas. And there's a couple different things you could say. You could say, oh, magnesium metal probably is not going to become a gas, so we don't need to worry about that. Magnesium chloride, also, given how heavy magnesium and chlorine are, probably not going to become chlorine ions. They're going to interact with water really well. They're probably not going to become a gas. HCl actually could become a gas, so we could use HCl as a correction here, but 6 molar after it's diluted through this entire thing, that concentration of HCl and that amount of HCl is actually going to be really, really tiny. You could even go as far to say, well, what if the glass has some off-gassing that creates some extra thing? Or what if I used a copper wire to hold my piece of magnesium there? What if that had some off-gassing associated with it? What if there's copper ion? No. It turns out the other thing that's most likely to cause some amount of additional gas contamination is just water vapor, right? We know that in the atmosphere around us, there's some amount of water vapor. So we can also do a correction for how much H2O gas there is. This amount of H2O gas so this pressure of H2O gas is really going to depend on the temperature of the water. Hotter temperatures, you get more water vapor. Lower temperatures, you get less water vapor. And there's an equation given on Canvas for how we do that. Also, this H2O liquid part, that's going to be height dependent. How high above the water level is the liquid inside of the eudiometer? I would say, and all of that's pretty straightforward. When we give you equations, most students do a fine job doing the plug and chug thing. A couple things that are important to realize. Units. That temperature needs to be in Kelvin. And if you're using the equation given, that height of H2O needs to be in millimeters, not the centimeters that we give it to you in. So make sure you're paying attention to your units. Additionally, just to be extra frustrating, the pressure in the atmosphere is given in inches of mercury, inches of mercury, I think. Let me double check that. Yeah, it's given in inches of mercury. This equation from the lab pal, or from the background, gives you pressure in torr. This gives you pressure in torr. And if we look at the ideal gas constant, we actually want this pressure in atmospheres. So we end up with this kind of, even though the equations are not hard to plug into, if we don't pay attention to units, we get messed up real quick. So we have to make sure we're paying attention to units as well. I like to convert everything to atmospheres because that's the unit we want this in because of the ideal gas constant we're using. The ideal gas constant, R, is equal to 0.08206 liters, atmospheres, moles, Kelvin. Right? And the fact that that gas constant we're using is in atmospheres is why we want to make sure that we end up with our pressure of H2 gas in atmospheres. And it is very sig fig dependent. Good catch, Ashley. It turns out that these corrections are going to be down in like the third decimal place, the second or third decimal place. So we have to make sure we're keeping enough sig figs to catch these corrections. Does that help out? Does that frame your thinking a bit better, Joseph and Nick?
That clears up a lot, actually.
Awesome. Great. Now that we've got this kind of the experimental idea out of the way, we're going to look at 5A, which I shouldn't have raised that, is really going to get to this idea of how additive volumes work when we're using the ideal gas law, right? And the idea here is that we say, imagine you've got 6.14 grams of each. So I had 6.14 grams, you might have something different. It's weird to give these gases in grams, but you've got argon, krypton, and helium. Argon, krypton, and helium. We can, of course, get this to a moles of each. And then from the moles, we are given a pressure. Sorry, we're not given a pressure. We're given a temperature and a volume. So we've got, we're going to be using PV equals nRT, where The temperature is given, the number of moles can be calculated, and the volume is given, and the ideal gas constant is known. So for each of these, we can set up this type of equation that says, like, the pressure due to argon is going to be equal to the moles of argon times RT over V. The pressure due to krypton is going to be equal to the moles of krypton times RT over V. And the pressure due to helium is going to be equal to the moles of helium times RT over V. And we're just doing this calculation 3 different times, recognizing that we've got them all in the same volume. And because it's that same volume, we're going to see each one contribute some amount of pressure. And because it's the ideal gas law, right, since this is behaving like an ideal gas, we can just directly add those pressures together to get the total pressure applied.
Okay, that makes sense. Thank you.
Okay. We just had another question come up. This was about practice problem set 2, number 26, which is asking us to find the average. Let's see. What is the formula for this ion? Use this notation CXHYOZ, but don't worry about the subscripts. So I'm assuming that this is referring to this structure. And so we want to know what the formula for this structure is. Taking the line drawing notation, recognizing that there must be a carbon wherever the line ends, and every carbon is going to be filled. And then we just have to count things up. So it's going to be C2, H1, 2, 3, 4, 5, H5, O. And we don't really put O1, like if there's an oxygen, the 1 is assumed. So we put C2H5O for that question. That was practice problem Practice problem 2, number 26. And then 26b is the average oxidation number for the carbon in the ion, which is the one you were actually asking about. So 26b says, what's the average carbon charge? I think I need information from an earlier part. Oxidation numbers. Ooh. Oh no, we can do this. Okay, so for this we have to know a couple things. We have to know that oxygen is likely a -2. Hydrogen is likely a +1. We've got 1 oxygen. We've got 5 hydrogens. And carbon is a variable value, and we've got 2 of them. But we know, let me check something real quick. Does this thing have a overall charge associated with it? So the charges aren't being shown. We're supposed to figure out what the charge on the molecule is from earlier parts. So we've got to go ahead and do that now in order to figure out this part. So in order to figure out the charge here, I'm going to, because I need to know what this is going to total up to. If it's neutral, it would total up to 0, but if this has charge, it's going to be non-zero. So I've got, sorry, I shouldn't have erased that. I've got each carbon. So now instead of thinking about the charges that it's likely to have, I'm thinking about the valence electrons that it brings. I've got 4 electrons from each carbon, and I've got 2 carbons. I've got hydrogens. I've got 1 electron from each hydrogen, and I've got 5 hydrogens. And I've got 6 electrons from each oxygen, and I've got 1 oxygen. So that's going to give me Oh, math in my head. 14 plus 9, 19 electrons. Now, so if it was perfectly neutral, I'd have 19 electrons in this structure, so we're going to count and see how many electrons we actually have to see if we've got extra charge. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So I must have one extra electron if I'm going to have 20 electrons in this Lewis structure. So if I've got one extra electron, this thing is overall a -1. And that was from earlier in the problem. So I know that this has to add up to a -1 overall. And now I'm going to just solve. I'm going to have -2 plus 5 plus 2x is equal to -1. And I just solve for the x, for that charge of carbon. I called the question mark, and I'll leave it as a question mark for consistency. Plus 2 question marks, and I just solve for question mark. So that's going to be negative, that's going to be, math in my head again. Add 2 is going to give us +1, minus 5 is going to give us 4. Well, no, calculator. I'm not trusting my head right now. My brain is thinking about something else right now. 1 negative plus 2 minus 5, divide by 2. So if I did this addition correctly, this little bit of algebra correctly, we should get an average charge on these carbons of 1.5. Now, one of these is likely to be, these two things are likely to have different charges associated with them. And it's really a question of, well, what's the charge of each thing? But we can just do an average charge pretty easily. The method for getting the charges of each thing is something we didn't really talk about this quarter, but will come up in organic chemistry classes in the future. And then we've got practice set 3. This looks like a quick conceptual question. Practice set 3. Categorize the reaction. So we're looking at this, and it's KF plus HCl goes to HF plus KCl. And it says, well, what type of reaction is it? And I'm looking at it, and I say, okay, is it a precipitation reaction? I have a pretty easy time seeing precipitation reactions. Let me write it on the board so we can work on it together. Is this okay, Ashley? Is it all right if I erase this?
Yeah.
Okay. So this is practice 3, number 3. We've got KF plus HCl goes to HF plus KCl. Everything's aqueous. And so it's pretty easy right off the bat to say, I have the easiest time seeing precipitation reactions because I'm looking for a solid being formed from 2 aqueous solutions. If I look at my solubility rules, everything's aqueous. So I'm not seeing a precipitate form, so it's not precipitation. Next up, it honestly doesn't look like an acid base to me using my Chem 124, 127 knowledge. So I'm going to check if it's a redox reaction. So I'm going to go and I'm going to figure out the charge of each thing. Potassium is a +1, fluorine is a -1, hydrogen is a +1, chlorine is a -1, hydrogen is a +1, fluorine is a -1, potassium is a +1, chlorine is a -1. I don't see any charge change. So it can't be a redox reaction either. Right? I'm not seeing anything that suggests I'm going to have a change in charge. So in that case, it must be an acid-base reaction. And then we can say, well, how could this possibly be an acid-base reaction? And this gets to what's the fundamental things we look for in an acid-base reaction. If we look at it in terms of, and this is getting to stuff that we do kind of in other classes, but if we look at it in terms of HCl plus NaOH goes to H2O plus NaCl. really what we're looking at is a hydrogen moving over to something else. And so this reaction actually ends up being acid-base because this hydrogen is going to move over to that fluorine, the same way that the hydrogen here moves over to the hydroxide. The reason this one's really hard to see as an acid-base reaction, and I think it's beyond what we'd ask on quiz 9, is because usually we look for water as a product, but that's not always necessary. Water as a product is really just what we see in our strong acid, strong base reactions. And so here, we're seeing a strong acid, weak base reaction where fluorine is still going to take up the hydrogens just like the hydroxide did, but it's going to be a weak base to form the HF. So it's still an acid-base reaction, but it's not one that we've really spent a lot of time talking about this quarter.
Okay, that makes sense.
For me, it's the process of elimination, go through the different possibilities.
Yeah. Okay. You keep saying that it's this is harder than what would be on quiz 9. So.
Not harder. I just said it wouldn't be.
But then what kind of things will be on quiz 9?
So, acid-base reactions that are more like the ones we've seen this quarter, so strong acids, strong bases, or carbonate reactions, acetic acid reactions, those would all be fine for a question in this vein. For the redox questions that we were, not the redox creations, the oxidation state questions, the average oxidation state is fair game. We could do questions like that, but we didn't really go over the individual atom in an organic compound oxidation state. We could do oxidation states in the polyatomic ions or ionic compounds, but probably not in organic compounds. So it's not that this is harder than what would be on the quiz, it's just adjacent to what would be on the quiz in terms of where we spent our time this quarter. Does that make sense?